Hi everyone. I would like to talk to you about bulk transport in samarium hexaboride with an emphasis on comparing samples grown by aluminum flux and floating zone methods. I want to thank my students who have done the experiments and my collaborators who have provided high quality crystals. We're gonna be using different transport geometries at high temperatures. We'll be relying on the well-known whole bar structures. At low temperatures, we're gonna use carbino structures. There is a challenge at low temperatures because the material has a surface conduction. So in order to extract information about bulk conductivity, we will be using inverted resistance measurements. The samples that we have, we always polish them and make these structures. Typically, the flux-grown samples are small, a few millimeters in size, and they always have aluminum inclusion. So we have to go to rather thin samples of about 100 microns or so to eliminate all the aluminum inclusions. This is not the case in the floating zone samples. The samples, we find them to be polishing much faster, and we have confirmed that some of the floating zone samples are a lot softer, maybe even about a factor of 2 or so, which is an indication that the samples might have maybe have off-stoichiometry. Now, let me start with the raw data. This is resistance from 8 samples that I'm going to focus on today. When you look at resistance, there is some variation because of the thicknesses, but overall, the samples, at least in the flux-grown set, is very similar to each other. And in the floating zone, I show 2 samples that significantly deviate. They have a lot more conduction at low temperatures. The conduction is not appears to be flat. There is some temperature dependence to resistivity, and such behavior have been reported in some of the other floating zone samples. When you look at Hall effect, and again, with Hall measurements, we're going to be focusing at high temperature to high temperatures, and we see a well-known sort of reversal of the Hall coefficient at high temperature. Instead of getting negative electron, negative Hall coefficient indicating electrons, we get a positive coefficient, which is due to the skew scattering. And when we compare the samples at high temperatures, we don't see dramatic differences, except these 2 samples at low temperatures again have different Hall coefficients. Now, I just want to briefly mention the Hall experiments. We have extended these to 400 Kelvin. We were expecting to see less of this resonance scattering because if the thermal broadening gets bigger than the KBT, gets bigger than the broadening of the F bands, then we expected to see again electron-like behavior, and we have observed that. Now, in order to analyze Hall effect, you cannot use the Hall coefficient at high temperatures. So what we ended up doing to get some measure of disorder or seeing what the mobilities of the samples were, we relied on RPES measurements and extracted some rough estimate for the Hall coefficient. And we knew the Hall coefficient is activated at low temperatures. By combining the 2, we said this would be a much more meaningful Hall coefficient. And if we use such a patched Hall coefficient, then we could get some idea about the mobility of all these materials. And when we do that, we found the mobilities to be very low. And maybe this is not surprising because the skew scattering is really dominant, and the mobilities at the are lowest when the gap is about to open up, and when you estimate mean free paths, they are getting close to the lattice constant of the material. There was one pathological sample which showed high mobility, or not high, but relatively high, and this one turned out to be the softest of the samples we had, and we don't particularly trust that particular sample because it might be highly disordered. Now, for low temperature characterization, we're going to be relying on both the standard Carbino measurements and the inverted resistance measurements. Now, in the standard geometry, at high temperatures, we're going to extract information about bulk transport, and we will extract the surface conductivity again using the standard geometry, and then we're going to extract information about the bulk conductivity by using the inverted resistance measurements at low temperatures. And when we combine the whole data, we will be able to extract bulk conductivity over a much wider range of resistivity values. In fact, in this particular example, we managed to expand the bulk resistivity measurements by additional 5 orders of magnitude. Now, if we have used this method to characterize samples with vacancies, they were grown intentionally with different boron samarium ratios. We found additional conduction at some of the samples, the origin of which we do not understand, but over a wide range of temperatures, the behavior found to be activated and rather immune to disorder. Now, we will extend these measurements to the floating zone set, and here is the raw data. And when you look at it, the 2 samples which we mentioned earlier indeed appear to be bulk conductors. We don't see this inverted resistance going down. 2 of them are definitely, the plateau is due to surface, and we do extract bulk conductivity using this method. And when you put them data together, you get more questions than answers, but roughly speaking, there is no question the floating zone samples always have more bulk conductivity. Sometimes it's so dominant that you can't see the surface conduction. And the behavior is not the same as the ones that I've shown earlier, where there was a flat plateau. And goal, of course, of our study is to go to the bottom of it to see what exactly, which disorder contributes to conduction. There are actually 2 candidates, one, and they might be both present. One is, of course, hydrogenic impurities, which we first thought they wouldn't be present, but there is a recent work by Brian Skinner suggesting that when you use the Mexican hat dispersion, then you would get hydrogenic levels with low binding energies and a new kind of impurity conduction, which we are hoping to investigate. And the other thing that we know, we particularly worry, is transportatory dislocations. We know dislocations must be present. For example, in this particular floating zone sample, there is known variation of the lattice constant, and we could relate the gradient of the lattice constant variation to the density of dislocations. Our original estimates range on the order of 10 to the 10 dislocations per centimeter square, for floating zone samples. And we have found these dislocations, the presence of dislocations using etching techniques. And when you do an etching, if you have the right etchant, you might get something called edge pit dislocations. These are sort of lower bounds for the dislocations, and indeed the floating zone samples, at least in this study, shows much higher concentration than the flux-grown samples. And these are not, we believe these are not the true carrier dislocation densities, but they must be present. So I want to conclude by saying that there is differences between floating zone and flux-grown samples. Floating zone samples have additional conduction. I don't think our experiments will solve, at this stage, we are not in a position to resolve the mystery of quantum oscillations, but we are going after these disorder driven conduction paths, both the possibility of transport through dislocations, as well as the predictions of Brian Skinner's theory.